Today I'm meeting up with Xabier Iturbe, and Xabier is responsible, he's project coordinator for a very interesting new development, a new chip design, a neuromorphic chip design. Good morning, Xabier, good to see you. I'm reading on your website, we are designing a neuromorphic sensing and processing 3D integrated chip. Very good. But tell me, I've been thinking about this. What exactly is the difference between a normal sensor and a neuromorphic sensor?
Well, first of all, I have to say that our project is about visual sensing, so all the explanations are related to image and video processing, not to other different kinds of sensing, which actually can also be neuromorphic, but we are not dealing with that. So in terms of image sensing, I will say that the normal image sensors, as you probably know, work on frames. So basically, at every given point of time, what you receive is the status of all the pixels that make up the sensor itself. Well, this is interesting, and this is the traditional approach, and it's fitting well with conventional processors, and especially with traditional AI models like convolutional neural networks, because these kind of networks, they basically operate on the state of all the neighbor pixels when extracting the features from those pixels. However, neuromorphic is completely different approach, and what they do is the intention here is to only detect significant changes in the incoming image. So basically, each of the pixels in the sensor is autonomous and is constantly comparing itself to the brightness that it's looking at. And every time that there is a significant change on the brightness of the light, what it does is that pixel generates an event. So if you think carefully, the paradigm changes completely, because at this time, what we are seeing is the patterns of activations of the different pixels. And this brings information not only in space, which pixel is activated, but also in time, when the pixel is activated.
Yeah.
So this concept actually, well, you can imagine it, this concept to be kind of a sparse volume of data that is spread in the X, Y, and T, right, in the time domain. This kind of data can actually the effect of sensing in this way the data, can be even more interesting when you deal with neuromorphic processing units. So when you do that, basically what you do is you try to extract all the information in space and time, also in the processing and the inference states. And here, probably the most interesting or best well-known approach is spiking neural networks, that try to be more biologically possible than convolutional neural networks. And they incorporate the timing also when doing this processing of the data.
Yeah, I hear you saying that basically it actually mimics this processor, how we as a human actually perceive light. I hear you saying space-time. That is something completely different approach than a normal sensor, which you're telling, where you have rays of cells which are actually read out. In your approach, you're actually, as I understand it correctly, have individual sensors, and that allows you to actually turn that data into more event-driven sensor, which basically reacts to not everything, but for specifically events, like what we're doing as a human being. We see a car coming, we see the sun, or we see a tree, and we can focus on that. Is that correct? Is that the way you are approaching this whole project?
Yeah. This is, I would say, a trend that is ongoing nowadays. It's something that started a long time ago, but it is, I would say, in the last 8 years when it has actually produced a boom. And there are a lot of startups and a lot of researchers working actively in this area. Yeah, so I would say that the project is quite timely.
Yeah. Now, with this, you're also told us that this approach, this sensor, will not work very well with the existing CPU architectures, where you have the CPU, you have the sensor, you have the data from the sensor, you have the CPU, you have the memory, and you're saying, why is that not working properly? What is the difficulty with that? Because we can do everything with computers.
Yeah, well, I wouldn't say that it's not working properly. What I would say is that you are actually missing the point and the opportunities for, well, first of all, to extract more information, not data, but information out of the data, because you are missing mostly the time domain processing with conventional CPUs. And the other thing is that you are losing or missing opportunities to further improve on performance and efficiency, because basically, this kind of data that is coming coding the time and space needs its own kind of architecture to actually benefit from the sparsity that this data is coming with. In a CPU, you have a lot of waste of moving data and instructions from the memory, and this will not be highly impacted by the benefits that this kind of event-driven data brings to you. So it's more like a loss of an opportunity rather than that they don't fit or that they cannot be run together.
Yeah, so that is one of the reasons why you're working on this 3D integrated chip. Basically, I see a 3D stack of sensors and computing and memory basically overlapping. How do I need to see this? Because what, in a sense, is the difference between a 3D integrated chip and a normal chip then? Because there will be computing, there will be memory, there will be data moving up and down, not left and right, but perhaps up and down.
Yeah, I would say that actually, when it comes to a 3D integration, it's not so much related to neuromorphic by itself, which obviously is better and is benefited more with neuromorphic data or event-driven data. But I would say it is more related to the images. Because if you think carefully, the image is naturally 2D. So it means that you can capture the data all together with different pixels, and the data comes in the 2D by itself. So if you go with a normal conventional integrated system, in which you probably will have only one data bus or one point through which all the data has to go through, this is a kind of limitation because you are collecting data in 2D, but actually moving the data in 1D. And that's why the 3D integration is interesting, because you can actually move data from different regions in the sensor using dedicated paths that connect to the downstream processing that is happening well below in different layers. So the interesting thing here, that is an important point in the project, is that we claim that we will be able to estimate early in the processing pipeline what is the information value of the different regions, and actually sense these regions starting from the sensor itself at the given resolution in terms of data, but also in terms of the time. And this is where the neuromorphic comes to the picture. Because as I said before, the time is something that comes naturally in neuromorphic sensing. And what you can do is say, okay, in this region, there is something that is potentially very important. So let's focus on that region and let's keep track of it at very short periods of time. Whereas in another region, maybe there is not so much relevant data, and you just want to have some kind of tracking for that region, but very from time to time, not very precisely in time.
Now you received funding from the European Commission to actually to start launching this this development and the development of this processor. How where are you in this process? Are you in research phase, or are you already doing some developments here? What is going on behind the screens?
I would say that the project itself, I mean, overall speaking, the whole concept is risky and belongs to the exploratory research area rather than consolidated technology that is ready to go to market in the short time. However, this said, there are some particular aspects of the project and some particular developments on the project that can benefit to individual or several partners. at a higher or more advanced, let's say, development status and approach in the market. So it's interesting in that regard because we work at different paces in different work packages, and the expectation can be different. But as said at the beginning of the answer of this answer, so the whole project, I would say, is kind of an idea, and what we are expecting is to benefit from the findings in different parts of the project that will probably follow up with further research projects, and eventually we hope that it is interesting and impacting the real commercial chips.
Yeah. Now I'm tempted to ask a stupid question.
Let's see.
Which is my speciality.
Okay.
I was thinking, many of the process we have as a human being are, how do you say it, analog based. Yeah. So our speaking, our viewing, etc. And in the past, I remember in the old analog days, there were analog computers. There are analog computing, analog systems that can react, etc. Have you ever considered that the whole approach of neuromorphic or this event-driven sensing can also have an analog part?
Yeah, this is something that is on the table. You are actually speaking to a digital guy, so probably he's not the best person to answer to this and to know the insights of what analog means on here. But clearly, analog by definition is the most efficient and also the technology that brings the latest latency. So there is a clear match between analog and neuromorphic, and even more, I would say that the real first stages of the device, this is where the light is transformed into electricity. This is by nature analog. So it makes sense to me to expand a little bit more the analog part with all the benefits in efficiency that it brings. However, I would say that first we need to make sure that the approach that we are taking makes sense. At digital, or even not digital, even emulation, simulation level, I'm talking about how to use SNNs for extracting the value on information of the different regions that I mentioned before. And once we are ready with this and we have some conclusions, I honestly believe that one path to follow is going analog and trying to implement this processing in analog. But this will be probably one of these follow-up projects that I mentioned before in my previous answer.
Okay, thank you. Because I think with your approach, digital approach, I see some claims also on your website that it will be 100 times more energy efficient to have this. The latency reduction will be 50 times, all estimates, of course. The energy is really, really low, and silicon area will be 50 square millimeters. These are the design objectives, I feel. And that is also with your approach, what you're looking at. When do you hope to get back to us with, okay, this is what we've done, can we do? Are you looking to actually develop some silicon here, or are you saying, okay, we do the research and then leave it over to the rest to do this?
Yeah, I mean, this is also related to my previous answer when I mentioned that different parts of the whole system are potentially different development stages and with potentially different objectives. And actually, some of the layers that we are planning, we plan to actually go to silicon and to create some test chips. The most interesting one, I would say, that is the sensor itself. So we are lucky to have very expert people in the area like Bernabé Linares from CSIC, and he has a long track of producing different test chips and incrementally increasing the complexity and exploring novel concepts, starting from a test chip that actually works. And this brings the risk lower, which is really important when you go to silicon. And yes, we will have this test chip implemented in silicon and ready to use by the rest of the system, in which most of the layers, as I said before, we expect to be on the prototyping FPGA kind of implementation and extract some conclusions from these implementations. When something important actually that you mentioned at the beginning of the question is about the performance and benefits numbers that we are expecting on here. And I would say we have to be careful on here. And if you see clearly how the wording that we are using for this in the website, we are always comparing to the state of the practice today, which is running CPUs and GPUs with frame-based data. So we compare against that. Obviously, there are a lot of different developments going in research, and some of them are super powerful and the expectations are super high, and we are not comparing to that. Yeah. If we want to compare to that, we have to take these other paths, as the one that you mentioned before, going analog or even going further. So the whole concept here, I would say, is novel. And the novelty of the concept is that by early discarding data without even processing this data, because they don't pose any information value, we expect to gain a lot of benefits in efficiency, latency, and performance. And this is something that is regardless whether the implementation technology is digital, analog, or whatever. So it's a concept itself. And this is one of the most important things that I think we want to test and to conclude in the project.
Okay.
It's useful for many other projects, not just for us.
Yeah. I understand. Thank you very much. I think I've had my questions, even my stupid questions. So thank you for allowing me to ask that. We're looking forward to more results coming out of your research and your development. Perhaps we should connect back again over a year or whatever to see what the actual state is. So thank you very much for your explanation. Thank you very much for your time.
Yeah, thank you, Xabier. I'm actually really willing to connect to you back, now that I can pronounce your name correctly.